Today we're talking about probability and probability distributions, and we are starting now the transition into inferential statistics. Woo! It's the kind of the real meat and potatoes of stats. As we get started, let's introduce some concepts first. The probability, because we're going to spend the whole day really or most of today hopefully, talking about probability. And there's a lot of different definitions for probability that you might see. I like this one from Ted. The probability of an event is the proportion of times that the event would be expected to occur in an infinitely long series of identical sampling experiments. So you can think of that if you did the same thing exactly over and over and over and over an infinite number of times, how often would something that you're interested in happening? That's the probability. So it's kind of a mathematical, conceptual sort of understanding. The couple terms in that definition I want to talk about. The probability of an event. You can think of an event as something like, for probability, we always think of gambling and that because gambling comes down to probabilities. So you think of the event is being dealt a 21 if you're playing blackjack, or rolling a 7 with a pair of dice, or landing on the $100,000 spot on Wheel of Fortune. Those are all, you can think of those as events that we're looking at the probability of that event happening. And sampling experiments sounds kind of very technical, whatever, but it's just stat speak for things like drawing a card. Is that sampling experiment? You shuffle the deck and you draw a card. It's a little experiment. Let's see what I got by sampling that. Or rolling a dice. Every time you roll the dice, it's a sampling experiment. May not seem like much of an experiment. It will not get you a PhD. But you can think of it as a sample. Nice try. You can think of it as an experiment. Or spinning the Wheel of Fortune wheel. You can also think of a sampling experiment, this it's election time, as picking a person for a survey. Okay? Those are all sampling experiments. Now, if all possible outcomes are equally likely, the probability of the occurrence of an event is equal to the proportion of possible outcomes favoring that event. It's another one like, okay, what exactly does that mean? So let's think about this. Break it apart a little bit. If all possible outcomes are equally likely, so what do we mean by that? That it's just a way of saying I'm not playing with loaded dice, right, or a weighted roulette wheel. Every possible outcome has the same chance of occurring. The probability of the occurrence of an event, that's just how likely is it that I'm going to roll a 7? How likely is it that it'll land on the 100,000? Or how likely is it that someone is going to say that I plan to vote for candidate Jones or something? Those are the probability of the occurrence of the event. It's just how often we think that is going to, the probability of that event happening. How likely it is that that'll happen. Kind of an easy way to see this is looking at kind of rolling 2 dice. And you can think if you roll 2 dice, there's 36, and then add up the values on the dice. There's 36 different possible sums that you could get. You can go from a 1 and a 1, snake eyes, to 6 and a 6, get a 12. Okay? So the probability of any total is just the sum of how many times that total happens divided by the 36 possible outcomes, right? There's 36 possible outcomes. So what's the probability of getting a 7? Well, we can just look and say there's 6 ways of getting a 7. There's 6 outcomes that give me a sum of 7. My event is 7. My event is rolling a 7. And there's 6 outcomes that can get me that 7. I can have a 1 on the first dice and a 6 on the second dice. I can have a 2 on the first dice and a 5 on the second dice. Each of those is a different outcome that lead to the same event of 7. The outcomes are all kind of ways we get to that same event of what is it that we're interested in. It's rolling that 7. So you can see probabilities then. The probability is just 6 divided by, there's 6 ways to get a 7. 6 outcomes that give us a 7. There's 36 different possible outcomes. So it's 6 over 36 or 1/6 or 0.1666666 are all ways of describing the probability. Well, they're all ways of reporting the probability. So notice right there, probabilities, what does that tell us about a probability? It can never be less than 0, right? Because you can't have a negative one way of rolling a 7. I could say, what's the probability of rolling a 13? Well, that would be a probability of 0 unless you've got some funny dice. You're playing like the Dungeon and Dragon dice. I got to remember, that could be fun. Is there some way to roll a 13? Well, look. Yes. So you can have a probability of 0, but you can't have a negative probability. And you can't have a probability greater than 1, right? Because the most you could have, if I said, what's the probability of rolling a number between 2 and 12, 36 outcomes, all 36 give me between 2 and 12. So it's a probability of 1. So if you ever see a probability less than 0 or greater than 1, you know there's a problem. Someone's done something wrong. We'll come back to this later on in the second half of the semester when we're reporting probabilities. Okay? In contrast, notice there's 2 ways we could roll an 11. There's 2 outcomes that give us the event of an 11. 5 on the first and 6 on the second, or 6 on the first and 5 on the second are 2 ways that we can get the 11. So the probability of an 11 is 2 over 36 or 0.0555555. Okay? Now, at this point, if this seems odd or even a little unfamiliar, then you should never ever go to Hollywood Slots. Right? If this is foreign to you, you've lived a very wholesome life. Good for you. So other ways we look at probability, and some of this you should be thinking, this sounds we've kind of already been here, and we're kind of retreading some old tracks in a slightly different language at the moment. Another way we look at probability is with flipping a coin. You can think of flipping a coin as a simple experiment with 2 outcomes. Do I get a head or a tail, right? And let's say I'm looking at the number of heads. And if I'm flipping 2 coins, right, there's 3 different events. If we think of, again, events are those kind of, what is it that the kind of a language perspective, I can have 0 heads, I can have 1 head, or 2 heads. If my question is kind of how many heads do I get, there's 3 events if I'm flipping twice. 0 heads, 1 head, 2 heads. So let's kind of write these down. Events, 0 heads, 1 head, 2 heads. And those 3 events reflect 4 possible outcomes. So we're kind of the language is might seem a little cumbersome, but again, in a way, the concept is what's important. There's 3 events, 0, 1, 2 heads, and there's 4 possible outcomes of rolling 2 dice. Right? I can have a tail and a tail. That gives me 0 heads. I can have a head and a tail, which would give me 1 head, or a tail and a tail.
It should be tail and a head.
Tail and a head. Actually, someone remind me. Someone take a little note so I can fix that slide, because there's already another typo I found later on.
The typo.
Expelliarmus. If you find other typos, let me know. Probability.
Okay, number 10.
This is.
Slide 12.
We could go back to like Zippity Doodah. It kind of doesn't have a probability. We could do a little Disney song.
What did you learn in statistics?
It's 12 on the printout, but
Yeah.
it's 10 right there.
Yeah, don't worry about the numbers. The numbers don't necessarily line up because I've already kind of made some changes. So we could have heads and tails or tails and heads. And those are two ways to get one head, or we can have head and heads.
So that's a different outcome, but it's considered the same event.
It's a different outcome that's the same event. In a way, it's like you're driving to this. I may regret this analogy. It's like I'm driving to, the Elton John show at the whatever Cross Center, which we did not see. And there might be multiple ways you can get there, but it's the same event, and there's other ways you can get there. I don't know. I have to think about it. I'm not sure I like that analogy.
I have a question about trying to figure out the number of events that are possible without having to draw it out like this.
Yeah, right.
Is there a mathematical way? So say I have 2 coins with 2 sides. Is there a mathematical way to figure out, do I just multiply them both? Do I multiply them all together, or do I have to draw it all out?
If we get into, if we really delved into probability, and some courses like this spend more time in probability, less in, it's kind of interesting how different books and whatever kind of, we're not getting as deep into probability as we could. So there are ways, but we're not going to worry about it. We're focusing on kind of at the conceptual level. If you're interested, I'm happy to talk. But there's formulas, permutations, combinations,
I was going to say, is that permutations and combinations?
that
Is
get
that
it some, that can kind of take this, take it up a notch.
Those were fun. I like those.
But for us, the book kind of, it's keeping it at a more introductory level for probability. But you can have whole courses on all sorts of probability. Good question. So then, now we can calculate the probability of each of these, right? Each outcome is equally likely, because we're not playing with a weighted coin, we hope. So there's 4 possible outcomes. One way to get 0 heads, so the probability of 0 heads is 1/4, or the probability, a p, is equal to 0.25. We have 2 ways of getting 1 head, so the probability of 1 head is 2/4, or 1/2, and 1 way to get 2 heads, so the probability of 2 heads is 1/4, or 0.25. We can visualize that with a graph, how many heads, 0, 1, 2. And over here is the probability of a head. And if you think about it, we've seen this before, but we were talking then about the proportions, not probabilities. We were talking how many, a quarter of the time, quarter of the people would do this, half the, so we're again, it's kind of very similar. Instead of talking about the proportion, we're talking probabilities. But you can see kind of how they're intimately related. That should hopefully already kind of get your head spinning that I'm looking at a distribution where we've talked about proportion above, below, we'll get to that in a minute, of a distribution. Now we're doing the same thing, but now instead of talking about the proportion of people above, we're talking about probabilities. So it's all intimately related. We could do this with 10 coins, or flip the coin 10 times. How many heads do I get? And again, it's gonna, if we calculated all those and we really wrote it out, this would be a nuisance to think of all the heads, tails. Trying to write this out, there's 1,024 different ways you could, different possible combinations. That's more than a few sheets of paper for the next assignment. But there are mathematical formulas that'll tell you exactly how many there are for each of those. So you don't have to do that. But again, the same idea that if we did write those 1,024 different outcomes, we could calculate the probability of each of those outcomes by just dividing how many times did you get exactly 10 out of 10 heads. Look, we know that. You can think about that. How many ways is there to get 10 out of 10 heads? Just one. Right, everyone's ahead. There's no other way to do it. So this would be 1 over 1,024. How many ways could you get 0 heads? Just one. Every single one is a tail. So it'd be 1 over 1,024. How many ways could you get 1 head? 10. The first one's ahead and the rest are tails. Or the second one's ahead and the rest are tails. The third one's ahead, the rest are tails. So this would be 10 over 1,024. 9's the same thing backwards, because now instead of, it may help to think of it kind of flipped, instead of it's 1's a tail. Everything's ahead except 1's a tail, and there's 10 different ways you can do that. So that'd be 10 over 1,024. Then it gets messier when you're dealing with 2 or 3 or 4. But anyway, so it's a distribution, right? We saw this as a distribution before. But now we're talking about it as probabilities. The probability of getting any of those specific number of heads. Now we're going to come back to this in a moment, but now let's look at a more example of a more complicated situation where you've kind of got 2 sets of events potentially going on.